Imagine you have a sample of an element like carbon, and you want to know what isotopes are in it, and you want to know what proportion of each isotope is in it. How can you do this? You can use mass spectrometry. Mass spectrometry is good for all sorts of things. It's good for identifying particular elements that are in a sample, for determining the isotopes that are in a sample, or determining the percentage of each isotope. You can determine the average atomic mass. You can look at atoms. You can also look at big molecules. Here's how it works. A sample is vaporized and exposed to a high-energy electron beam that causes the atoms or molecules to become electrically charged. They usually lose electrons. Now, the positive ion passes through an electric or magnetic field that deflects it. It bends it. How much it deflects it depends on the charge and depends on the mass on the ion. Heavier things deflect less than lighter ones. The ions are detected, and a graph of the relative number of ions generated versus their mass-to-charge ratio is made. We call this a mass spectrum. Let's start by looking at the mass spectrum of zirconium. We see a graph, and we see a bunch of peaks on it. The relative size of the peaks on the graph gives us a direct measure of the relative abundance of the isotopes in a natural sample of this element. Basically, what this means is the taller the peak, the greater the relative abundance, the more of the isotope there is. Now the x-axis, which has an m/z, that indicates the mass-to-charge ratio. For our purposes, we can think of the mass-to-charge ratio as the atomic mass of the isotope, the protons plus the neutrons, because this is what we're usually going to be seeing on the AP exam. In this example, the relative abundance, the y-axis, is reported in terms of the percentage of the sample that's made up of that isotope. So this is pretty straightforward. Zirconium-90 makes up about 50% of our sample. And if we added up the percent abundances of all these isotopes, we would get 100. But not all mass spectra are reported like the ones in the example we just saw. Sometimes the peaks are in percentages and add up to 100%. Sometimes the tallest peak is arbitrarily given the value of 100. Sometimes the peaks represent numbers of atoms. We often see this when we're dealing with very rare elements. Okay, so let's take a closer look at zirconium. From the mass spectrum, we can see that zirconium has 5 naturally occurring isotopes. The most common isotope is going to be the one with the largest peak, the one with the largest relative abundance. And in this example, it's the isotope with the atomic mass of 90. If we wanted to find the average atomic mass, we could easily do it using this equation. It's the same equation we used for calculating the average atomic mass, considering all the isotopes. In this example, our average atomic mass is going to be 91.318 after we substitute everything into our equation. And I went ahead and rounded that to 2 significant figures. In this next example, note that the tallest peak is arbitrarily given a value of 100, so we don't have this in terms of percent. We're going to have to deal with this a little differently if we want to know the relative abundance. We see that unknown isotope 10 has a relative abundance of 23, and unknown isotope 11 has a relative abundance of 100. This is the isotope that's the most abundant in this sample. Now, we're used to thinking of relative abundance in terms of percentages, and we can easily calculate the percent by dividing each number over the denominator of 123. So the next thing we're asked to do is to find the average atomic mass, and we're going to use our average atomic mass equation. We plug our numbers in and we find that our average atomic mass is 10.8 atomic mass units. And if we take a look at our lines up there, that makes sense that it's somewhere between 10 and 11 and closer to 11. Now the last thing we have to do is figure out what element this is. And what we're going to do is we're going to go to the periodic table. We're going to look at the average atomic masses of the various atoms, and we see that the one that's closest to 10.8 is boron. Now when you get these kind of questions, it might not be perfect. You look for the one that's the closest. But in our case, boron is the one that makes more sense. Now when you're doing these types of problems, there are 4 typical questions that you may be asked. One of them is which isotope is the most common, and you're going to figure that out based on the height of the peaks. The tallest one is the most common. What is the average atomic mass? And you can calculate that like we did in the last couple problems. What is the element? We did an example of that one. And what is the natural abundance? That's going to be what percentage of the total does that isotope make up. So in summary, we can use mass spectrometry to identify a particular element in a sample, to identify an isotope, or determine the percentage of each isotope in a sample, or to determine the average atomic mass of a particular sample of an element.